Good day once again, and you're welcome to the Libra Academy channel. In today's episode, we'll be looking at the concept of radioactivity. Now, before I go into that topic, I'd like to inform all our followers and viewers that some topics that we'll be discussing on this platform, we will not really be touching some aspect of those topics. Our reason is that we normally gather information from students, and we due to our research, we will discover that there are some aspects that students find very, very difficult in some topics. While other aspects they can easily read it on their own and understand. So we used to lay emphasis on those aspects that we feel like students find difficult, especially the one that involves calculation, and just leave other part that students can easily read and gather information and get themselves. So that being said, radioactivity. Radioactivity is a topic in nuclear chemistry or in physics, nuclear physics too, where we'll be having some disintegration of radioactive particles. So, what is radioactivity itself? Radioactivity is a process that occurs when an unstable isotope disintegrates and emits radiation. When an unstable isotope disintegrates to emit radiation. So that is just radioactivity. Now, what do I mean by unstable isotopes? There are isotopes of radioactive element, especially. When you have a radioactive element, the nucleus will be unstable. When the nucleus is unstable, it breaks to form new substances. So the process of breaking is what we call radioactivity. And in the process of breaking, it emits radiation. So that's where we're going to start from. What are the types of radiation that are always emitted during radioactivity? We have three types of radiation that are the main types. But in addition, I'm going to add two. We have number one, alpha particle. Alpha particle, which is always represented by an helium atom, 4, 2. That is an alpha particle, and they are positively charged. The second radiation that can be emitted is known as beta particle. Beta particle, they are represented by electron, E0 minus 1. This is the representation. E that stands for electron, 0 minus 1. And it is always negatively charged. The third type of radiation that can be emitted is what we call gamma ray. Gamma ray is an electromagnetic ray, and it can always be represented by something like Y symbol like this. Now, Y is neutral, which is gamma. Gamma is represented by Y symbol. It is neutral in charge. Now, these are the three main radiation that can be emitted during radioactivity. In addition, we have what we call proton. Proton, which is represented by hydrogen, 1, 1. I will still explain all these subscripts and superscripts. So leave it like that. We don't need to discuss the charge. We have another one that we call neutron. Neutron is N10, like this. We have deuterium. Deuterium, which is H21. And we have tritium. Tritium, which is H31. Like that. All these are radiations that can be emitted during radioactivity. Now, what are all these 4, 2, 0, minus 1, 1, 1, 1, 0, 2, 1, and 3, 1? Now, normally in chemistry and even in physics, we have this. Let's represent an element with this symbol X. If this is an element, so to say, it will have what we call mass number, which we normally represent by letter A, and atomic number, which is normally represented by letter Z. The mass number is always a superscript, while the atomic number is always a subscript. So if you have He42, like that of helium, it means helium has mass number of 4, and it has atomic number of 2. Atomic number of 2. So the superscript represents mass number, while the subscript number represents atomic number. So that is what all these 420 minus 1 means. So these are the radiation that can be emitted during radioactivity. All right, now we need to move. We have three parts in radioactivity. Three parts. The first part is the explanation of radiation and some terms like half-life. Half-life. What does half-life mean? When you call something half-life, you can see, like the name implies, half-life, like half of life. But this time around, this half-life is not as it is written. It is explaining time taken for half of a radioactive substance to decay. Time taken. Time taken for half of a radioactive substance to decay. That is what we call half-life. Now, we have another term like emission. Emission is just from the word emitted. When something is liberated or emitted. So that is what emission means. We'll still come back to these terms proper later. We have another one like fusion. Fusion is when two things are fused together. And when you are bringing two things together, fused together, two things are bringing them together to form one. That is what fusion is explaining. Why fission is simply put regarded to as splitting. When one thing splits into two, that is what we can refer to as fission. All right, now, having said all this, we have some other terms that we need to explain before we go to the next part. This first part that I'm explaining is the part that concerns explanation and definition of some terms. Now, we can divide radioactivity into two. We have the first type, which we call natural radioactivity. Natural radioactivity. In natural radioactivity, what do we have? One thing that you always use to identify natural radioactivity is what we call spontaneous. When you hear spontaneous, it means that thing is occurring naturally. It is occurring automatically without inducing the reaction. It's going to occur. Another thing to get natural radioactivity is emission. Emission. It is only in natural radioactivity that we still have emission. What do we mean by emission? Now look at the reaction above. We call this type of reaction nuclear reactions. We have U238, U23892. This U represents an element known as uranium. Uranium with mass number of 238 and atomic number of 92 undergoes natural radioactivity or undergoes emission or undergoes decay or undergoes disintegration to form thorium, TH, 23490 plus He42. Now, if you look at this reaction, one thing that I want all of us to take note is that these particles here, this is an element, a radioactive element. This is another. Thorium is also a radioactive element. But helium here is a radioactive particle. It is a type of radiation. This helium here, a type of radiation, which we all know as alpha particle. Now, you will discover that we have a radioactive particle or a radioactive radiation at the product side of the equation. Look at it properly. Uranium splits into thorium and helium, whereby helium is representing a type of radiation, which is alpha particle. Whenever you see a type of radiation, especially alpha, beta, or gamma, at the product side, it is natural radioactivity. That is explaining emission. It means, I gave definition earlier that radioactivity, it is a process whereby the nucleus of an unstable isotope disintegrates by emission of a radiation. Now, the nucleus of uranium now disintegrates to emit an alpha particle. That is emission. It has emitted a radioactive particle or a radiation, in short. It has emitted a type of radiation if you have it at the product side. So this represents natural radioactivity. And as a matter of fact, if you check very well, the total mass number at the reactant side is also equals to the total mass number at the product side. This is 238. 234 plus 4 will give you 238. The total atomic number is also the same. 90 plus 2 will give 92. This is a nuclear reaction representing a natural radioactivity. What about artificial? In artificial, it means it cannot naturally occur. You can call it induced. Artificial or induced radioactivity. It is just the opposite of what happens in natural. And here, we'll be having words like bombardment. Bombardment. Bombardment is the word to describe artificial radioactivity. The same way we have used spontaneous and emission to describe natural radioactivity. So, a suitable reaction to explain artificial radioactivity is this reaction of nitrogen, helium, give oxygen plus a proton. Now, if you look at this equation, we have nitrogen reacting with helium, which is an alpha particle, to produce an isotope of oxygen. I know you are expecting the mass number of oxygen to be 16. We actually have three isotopes of oxygen. There's one of 16.8, there's one of 17.8, there's one of 18.8. So here we are making use of the one of 17.8. Now we have proton as well. Now, in this case, if you look at this one, we have this first reaction. We have the radiation, which is the alpha particle at the product side. But this time around, we are having it at the reactant side. So whenever you have it at the reactant side, it is explaining what we call bombardment. So in this case now, we can say that nitrogen is bombarded with helium to produce oxygen and a proton. So this one is artificial because without bombarding nitrogen with an alpha particle, it's not going to produce oxygen and a proton. As simple as that. That's what the difference between natural radioactivity and artificial radioactivity. And again, that is another difference between the nuclear reactions. So whenever you come across a reaction where the radiation is at the product side, it symbolizes emission and it indicates natural radioactivity. Whenever you have at the reactant side, it indicates artificial radioactivity. So this is the second part that is explaining the types of radiation and the types of nuclear reaction. Now, another thing is balancing of nuclear reactions. If you look at this now, it is balanced because we have 14, 4, 17, 1, 18, 18, total mass number. Total atomic number is 17, 2, which is 9, 18, 1, which is also 9. So you must be able to balance nuclear reactions. Let's balance some nuclear reactions. Now let's take this example. Cobalt 60 undergoes the following transmutations by emitting alpha particle to produce isotope A. Isotope A then emits two beta particles and one alpha particle to form isotope Q. When isotope Q is bombarded with deuterium, an isotope G, a neutron and a gamma radiation is produced. Then we have the question that you should represent the information using nuclear equations and that we should identify isotope A and G and state the relationship between isotope A and Q. Now, this is the interpretation of that question in a nuclear equation. Cobalt 60 undergoes emission. When you hear the word emission, it means your radiation will be at the product side, like I said earlier. When you have emission, it means you are going to have that radiation at the product side. So cobalt 60, 27, the mass number is 60, the atomic number is 27, emitted helium. So we are going to subtract 4 from 60, then we have 56 left. We'll subtract 2 from 27 and we have 25 left to form isotope A. So isotope A has 56 mass number and 25 atomic number. That is the first statement. Then that isotope A also undergoes emission. And this time around, it is emitting two beta particles and an alpha decay. Before we will know what will be formed, we must first subtract the property of helium and two beta particles from isotope A, which was the result of the first emission of cobalt. Now, we have isotope A with 5625, 56 mass number and 25 atomic number. So two beta particle. Now, let me pause here to explain that beta particle will not affect mass number of a radioactive particle or any particle undergoing radioactivity. The mass number is zero, so it's not going to affect the mass number of that particle. And the atomic number is -1. It means it's going to be increasing the atomic number of that particular substance by 1 if it is emitted, and it will be reducing it by 1 if it is bombarded. So this time around, it is emitted. Beta particle is emitted, so it means it's going to increase the atomic number by 1 because it is -1. If you transfer minus from this side to the other, so if -1 is transferred from product to the reactant side, it adds to what we have here because it's going to change to positive. So that is why beta particle will always increase atomic number by 1. So, having said that, let's go back to our solution. We have isotope A, 5625. It means the mass number will remain unchanged when it is emitting beta particle. Now, this time around, we are having two beta particle. It means 2 multiplied by -1 will give us -2. So, it means it increases from 25 to 27 when it emits this particular beta particle. Now, on getting to alpha particle, this remain unchanged. Don't forget, this has increased to 27. Now, this will still remain unchanged until when it gets to beta, that it will now decrease by 4. So it means from 56, it decreases to 52. From 27, it now decreases to 25 because we have to subtract these two from it. That's what formed this isotope Q. Now, lastly, we are going to bombard Q with a deuterium. Deuterium is an isotope of hydrogen, but having a mass number of 2, atomic number of 1. So, bombardment, this time around, it means we are going to have that particular radiation at the reactant side. At the reactant side, bombardment, reactant side. Unlike these two that were emission, they were emitted at the product side. So, this 25 now plus 2 is going to, 52 rather, plus 2 is going to give us 54. But don't forget in the question mentioned that we are bombarding with deuterium and emitting neutron and gamma. Gamma is not going to affect substances, it's not going to affect the atomic number, it's going to affect the mass number. It is neutral, it doesn't affect in terms of mass and atomic number. So it remains the same thing. So it was sent in the question that Q, isotope Q, it was bombarded with deuterium and it emits neutron and gamma. Like I said, gamma is not going to affect. Neutron is going to affect by decreasing atomic number by 1. Neutron is going to affect by decreasing mass number by 1, and it doesn't affect atomic number. But at first, we need to add these two together. This time around, our deuterium is not decreasing. It is increasing because it is at the reactant side. So total mass number at the reactant side is 54. Total atomic number is 26. Out of the 54 that is total mass number, neutron is going to reduce by 1 to 53. Then the 26 of the atomic number remains unaffected because gamma is not going to affect in any way, and neutron does not affect atomic number. That is why we have G to be 53 and 26. So this is the representation of that question that we have in a nuclear reaction. And any nuclear reaction you are going to be coming across, these are going to solve it. Don't forget, when you have emission, it means you are going to have that radiation at the product side. When you have bombardment, you will be having that radiation at the reactant side. So before I round up the video, let me just give you the formulas to solve any calculation under radioactivity. I'm going to just give you 3 formulas to solve calculation under radioactive decay. Number 1, when you are asked to calculate something like half-life, which we all know as TR. This is the symbol for half-life, right, as TR. TR is equals to 0.693 over lambda. This lambda represents decay constant. Now, the other formula, we have n over n naught, the lane of the two, lane of n over n naught to be equals to minus lambda t. Now, this t is different from this t. This t here is half-life, while t here is time taking. It is not half-life. Decay constant, this n represents final amount of the substance, while n naught represents initial amount of the substance. Then sometimes you may be asked to calculate activity of a particular radioactive substance, which is represented as the n over the t, and it can be calculated using lambda n. Lambda remains decay constant, while n is the final amount of the substance. So, if you have any question concerning radioactivity, you can drop in the comment section. You can also click on the link on my profile to talk to me on WhatsApp. Thank you.